manager Billy Beane, they started winning many more games. And it's widely attributed to his ability to scout out the best players using analytics. So here we see that this is the general manager Billy Beane, and in 2002 the A's, so that's the team name, Oakland Athletics, they lose Jason Giambi and 2 other stars, yet they made it to the playoffs with, as well as winning 20 consecutive games. So this manager Billy Beane, he was with the Oakland Athletics from 1990s to around 2002, 2003. So I think he performed all this analytics before it became popular, like before the use of analytics became popular in sports. Then next, so these are just some of the baseball terms. So there are 2 leagues consisting of 15 teams. Each season there is 162 games. The top 5 teams make it to the playoffs. So this is one of the variables we would be looking at later, like which teams could make it to the playoffs based on wins or runs scored or some of the other baseball analytics. Okay, so the goal was to make it to the playoffs. So he would find the best players that would help the team make it to the playoffs. Okay, rules of baseball, this and this. So maybe we can just take a look at, let's say, this graph that they collected data for. There are some players that, most players that cost a lot, they even within the 70 million to 90 million range, they have a wide variability for the number of wins. Like you could be paying 80 million to someone who only won 72 games, for example, which is not the best use of money in terms of managing which players to hire. Whereas there are some players like the dot in green, his salary demands are quite low compared to the number of wins he is able to achieve. Okay, these are just some of the wins and losses. So in 2002, after that, the manager retired. So as we can see, the number of the wins percentage started dropping, and also other teams started using more analytics to hire the best players. So of course, when there's less competition, his method works more successfully, but when everyone is using it, then the competition for the players is tougher. Okay, and here is 2002 is when their star players left. Yeah, maybe everyone realized his trick of hiring players and they replicate his trick, and so he doesn't have a competitive advantage anymore, which he held for about 5 years. Okay, then there's this other guy, Paul DePodesta. He also was part of the management team to hire the best players. So Billy Beane was 1998, Paul DePodesta was 1999, then they had a successful run with the Oakland Athletics, and so on and so forth. So they were the ones that helped make analytics in sports really popular. Yeah, because at that point in time, 1998, I don't think Singapore even had many computers. So so they probably performed the analysis on either some very expensive computer for that time, or maybe they just used like handwritten data somewhere, collected handwritten data and processed the data somewhere. So it's very different from what we have today. Okay, so these are just some of the terms. Batting average is number of hits over number of bats, blah blah blah. The only thing that is important here that I want you guys to take a look at is the OPS. OPS equal OBP plus SLG. So why this is important is because we have a variable that is linearly dependent on 2 other variables. So when we perform analysis, there will be like warnings in R saying there's linear dependence or multi-collinearity. This will be part of the warning in the R files later. Okay, then I'll move on to the R files. So the one we have today is moneyball.rmd. Okay, here we will just take a quick look at the variables. So W is the number of wins. Oh, we start with team, name of team, league, either American or National League, the year 1999 to 2012. So we see here we have extra data compared to what was portrayed in the movie. They were only there from 1998 to 2002. Whereas here we have extra additional data. Then games, the number of games in that year, number of wins, runs scored, runs against, OBP, SLG, and so on. Then here we have the playoffs. Just now in the slides we were talking about the playoffs. We want to predict whether they can make it to the playoffs based on the number of wins. Then we have the rank in season, the rank playoffs. Okay, so for example, with this data, maybe we would predict like, the batting average, maybe it's the most important metric to hire players if we want to maximize the number of wins. Or maybe the run scored is the best metric to predict the number of wins, and so on. Okay, then here, let us first read the data. This is our standard code. Every time we often provide CSV files, and you just need to read it into R. Okay, so rather than just looking at this summary, okay, I guess the summary, sometimes it's useful to look at the summary because to see how much variance there is within the variables as a very brief way to validate the data. For example, OPS, I remember it was percentage of something, percentage of slugging or something like that. Then we see here that the minimum is 0.637, maximum is 0.851, so the data is like, I would say it's okay. I don't really know what these numbers mean, but if I see a negative percentage or I see a percentage that is greater than 1, then I might relook at this OPS data before continuing with the data analysis. So we need to at least just a quick look to validate the data. Okay, then the rank in the playoffs, we can see the rank, there's only 5 teams in the playoff because the rank is either from 1 up to 5. Then there are also some NAs, so this assumes that the other teams did not play in the playoffs, so they do not have a rank there. Okay, so first thing, what would it take to make it to the playoffs? First, we'll just subset the data so that we only have data that this guy had. So up to year 2002. We just subset up to year 2002. And here. Okay, then in terms of plotting, we can just do a plot, and we also here this scale color manual, we saw it last week also. And so this means we add a legend to whether the team made the playoffs or not. So orange for made it to playoffs and black for did not make it to the playoffs. And we also add these 2 lines, x-intercept at 95 and 85, because it seems at this line 95 almost all teams made it to the playoffs. Then then lesser than 85 no team made it to the playoffs. So we just add 2 lines to just to classify the data, just initial prediction. So easy way to make an initial prediction: if the team had less than 85 wins, they would not make it to the playoffs. Okay, then next here. Okay, here we plot the wins against run difference, RD, and we see there is quite a strong linear relationship between these two variables. So we can claim that the run difference is a strong predictor of the number of wins. Since we can see, just visual inspection, we can see quite a strong relationship. And if we take a look at the summary, so I mean this code is, you'll probably see this a lot. LM, we plot W as the independent variable, and anything on the right of the tilde sign as the dependent variable. So wins against run difference, and yeah, data we'll use the 2002 data. And here, so yesterday someone asked me about it also. Here, what this p-value is, p bracket greater than absolute t. So this is the p-value for the t-test. We are always running a t-test, use like the first part of this function, the results of this function always gives us the t-test first. So this is the p-value of the t-test, which means we reject the null hypothesis. And here is the p-value of the, I think we are using the chi-squared test. So this gives us the F statistic and the p-value of the F statistic. So if I just Google the graph, F statistic graph. Okay, so if we just take a look at the graph here, okay, before that, here there are some values, right? 891 on 1 and 88 df. So this 1 and 88 matches the numbers. It matches the numbers here, n and m. This 1 and 88 matches n and m. Then the shape of the graph depends on the n and m. So it depends on n and m here. And based on the shape of the graph, we use the F statistic to get the area under the graph. So for example, I'll just so for example, if we have, let's say this one here, 10 and 4, then our F statistic is, let's say, 3.2. Then we would get the area under this, like the area here onwards. So this would be our p-value, the area under graph after the F statistic. Okay. Yeah, so that's what this p-value represents. It's the area under this particular graph, 1 and 88, and anything to the right of 891 on the x-axis. So it also tells us whether to reject the null hypothesis that the variances are the same. Like the variance of this, whether the variance of this run difference affects the model. Okay, then I've added in some code for ANOVA. So the F statistic is the mean squared error, the residual mean squared error over the total mean squared error. Okay, then I added in this also. So this I just wrote this line based on the output here. So so you can match the values if you want to check. Then also here, something different. So there are two ways to run the F statistic test. So the first way, which we saw earlier, is summary of model. Then the second way is to run ANOVA of the model. Okay, so here for summary, they would compare. So for example here, let me just run summary first. Summary. So summary would compare the t-test would be for testing whether the RD is significant if you remove it. Whereas if we run ANOVA, it would test whether the t-test is significant if you add the variable. So they are slightly different. Here I've written down the difference here. So summary is wins against run difference plus OBP versus wins against OBP. So this summary is if we remove the run difference, how would the data look like? Whereas ANOVA is if we add the run difference, what would the data look like? So these are all t-tests. Later we will discuss how to select the model. There are just some functions to run all the different combinations of the variables and pick the best one. Because it's not very obvious whether we should add or we should remove in this case. So if you are using ANOVA, by the way, the ordering of variables matter. You would add OBP, then add run difference. So you would add the items in order for ANOVA. So the ordering of the variables matter. But if you are running summary, then it doesn't matter because they would count everything except for that one variable. I don't think in particular this is tested since Prof, I saw he written ANOVA on the board and he cancelled it. So I don't think this is tested, but I just wanted to add it in so that it's clear what this is talking about. They test the t-test with and without the variable and see how beneficial it is. ANOVA, it stands for analysis of variance. F-test, for example, t-test, we usually compare whether the means are the same or not. Then ANOVA is, we compare the variance is the same or not. Yeah. So t-test is compare mean, ANOVA is compare variance. ANOVA is F-test lah, anyway. Then here, so for linear fit of the model, we can have this formula from the coefficients. We have W equals 80.92 plus 0.099 RD. I guess this one may be useful, just to show you where the numbers come from. I think in Excel you can also, if you plot a graph, there's like a function that you can plot this graphs also. Like in Excel, you can plot this graph, then at the top right or something, you can click. There's some option that you can add the equation of the line. So in R, we don't directly add the equation of the line here, but rather we just take a look at these values here. We just say that this graph is so W against RD equals W plus 80.92 plus 0.099 RD. So this estimate, the estimates here give us the equation of the straight line graph. So this straight line graph is based on this equation, 80.922 plus 0.099 RD. So I just typed it out here. So once you have this equation, given the wins, you can get the value of RD. Given the value of RD, you can get the value of wins based on this straight line. So we are just substituting in values for this straight line. And here, okay. So on line 94 here, we create some different models, each with just one independent variable, just to see. So in this case, we are manually testing one variable at a time. Later, we'll give a function that can test all the different combinations. Here, we are just testing one at a time, and we see. Oh, sorry. Okay, then here, adding OBP makes the model better. Then adding SLG also makes the model better, since there are 3 stars. So we can't say that we can't ignore it in a way. If we ignore it, then it's worse. So OPS also has 3 stars, BA also has 3 stars, so they are all significant based on this t-test at the 0. It's just 3 stars here, so it would be so 0.001. Yeah, then again, they'll always provide the F statistic and also which graph to choose, which is 1 and 88. Then 173 is obviously very far right, so the area under graph is very, very small. The area under graph is very small.
Basically, what it means is that p-value is less, then that means it's not null hypothesis.
Yeah, not null hypothesis. That means significant.
It's not a random chance.
Yeah, correct. Okay, then here. So here, this is the library to do the subset selection. So for example, if I just run this, let's see. Okay, here we run, okay, we can take a, before that, we take a quick look at the documentation for reg subsets here. We can use method exhaustive, backward, forward, sec, wrap, and so on. So maybe here we can just run method exhaustive. Method exhaustive. Okay. Then here we can see, we take a look at this this object over here, mreg data. For example. Okay, so here, so this gives the different combinations. Like, okay, wait, it's not, can't really see it from here. Let me just run the code. Okay, so here we see that they tried different combinations of these 4 variables. So they tried different combinations, and they also, just now there was a warning somewhere. Wait, what? Yeah, there was this warning here. They say there is a linear dependency found. So these little stars over here, they won't select OPS when OBP or SLG is selected, because they detected a linear dependency. So in test 1, they just add OPS. In test 2, they put OBP and SLG. In test 3, they put OBP, SLG, and BA. So this function is to run all the different tests and give you some statistics on each test. Then from each test, so here in this case there are 3 tests that they run, and we can, so the model we can choose based on a few different criteria. I feel it's more of a choice. In this case, the code originally we were talking about the CP, mellow CP, or also the AIC. So minimizing the AIC. So if we take a look at, if we just run this particular line, we would get these values here. So we can see that the second value is the lowest. So what this means is that having option 2 here minimizes the mellow CP. So it's just in general the best model to predict the number of runs scored. So if runs scored against OBP and SLG, we would have the minimum mellow CP. And the second line here is the adjusted R square. So it also has the best adjusted R square. So in this case, we would pick model 2. So this function here is just a way to collate your data for each of the different models. Otherwise, of course, you can do it manually. You can put run scored against OBP, run scored against SLG, and so on. You can type it in yourself, but running it through this reg subsets function will help you collate your data and provide the CP, so we can see what is provided here. gives you RSQ, R square, adjusted R square, CP, BIC. So they run the linear model for all the different combinations and collate the data for you so that you can select the subset of variables that we should use. So in this case, yeah, they tell us that OBP and SLG is the best. And why is this the best? Because it minimizes the AIC or mellow CP and maximizes the adjusted R square. So if we were to create a model, if we were to choose which variables would predict the run score, we would choose OBP and SLG. Okay, so far it's okay, or should I go through anything again? Okay, okay. Besides, okay, so running the model for OBP and SLG, here we have I typed it somewhere. Okay, I typed it. I typed it here. We have run score is minus 1014 plus 3562 times OBP plus 1413 SLG. So in terms of interpreting these numbers, we can see that if we increase the OBP, the run score increases more than increasing the SLG by about a factor of 2. So for example, if this, I think it's the Billy Bean, if Billy Bean wanted to hire someone, he would be willing to pay more for OBP than a SLG, since 1 point of OBP increases the run score much more significantly. Okay, so increasing OBP by 1% increases the run score by 35. So here we also just run analysis for the opposition performance. So it's we just use since we are given the opposition performance, we might as well see how the opposition performance affects the runs against. Okay. So here we can just see that, like OOBP and OSLG, the opposition performance also strongly predicts the runs against. So that means this particular data is important to look at when hiring a player. So of course, maybe there were some that were not important. For example, the batting average here. If it's not important, then we are not willing to pay extra for a person that has a good batting average. Even though other people may analyze that it helps statistically, we can show that this is not a significant predictor of the run score. Okay, then here, I'll just skip this here. Okay, so using model 5, wait, not this. Okay, yeah. Here we can just have a prediction. So prediction is just substituting in the numbers for the straight line. So just the equation of the line. We get the equation of the line, we sub in whatever values we have here. In this case, we substitute in OBP of 0.039 and we substitute in SLG of 0.43. It's just once we have the straight line, once we have the line of best fit, we can just substitute in any numbers for OBP and SLG to get a prediction for the run score. So before this, in general, we also want OBP and SLG to be within the range of data we have, so we don't like extrapolate randomly. Let me just I think maybe it's obvious, but I'll just draw it in. So for example, if we have, for example, from the best fit line here, okay, just from the best fit line here, if we want to use RD, if we want to use RD to predict W, we can predict from the range of RD minus 200 to 300. If RD is 500, we don't know if this relationship still holds. So we try to use the prediction within the original range of data. Then we will be more confident of our results. Otherwise, if we start seeing some strange results, we could say that, oh, it's because outside of 300 run difference, the performance varies different from the rest of the regular playoffs. So in this case, 0.039 and 0.43 is, I think it's within the range of our data. So the range of our data is 2 OBP. Okay, so the range of our data is 0.3. Yeah, OBP is generally around 0.3. So 0.339 is okay. And SLG is around 0.4, so that's fine. So it's within the range of our data. So we can just substitute in the coefficients and also substitute in our values for this particular player. And we'll get a prediction of the number of runs scored by him. I guess, like, I don't know, in a game or in a year. Okay, so here, 800. So I'm guessing it's in a year. I don't think you can score 800 in a game. So you can score 800 runs per year. Then in the book, he predicted it to be between 800 and 820. Again, I think we are using the same data set. So we do have the same predictions now as we do back then. And here we can just run again for a different value, 0.307 and 0.373. And we will get the number of runs scored based on this OOBP and OSLG. Okay, then we can predict run difference using run scored and run against. So if we have run difference of 179, we can predict the number of wins. Then remember, if we have 98 wins, we were quite sure to make it to the playoffs. From the graph, more than 95 wins usually make it to playoffs. So in this case, with these players, we are likely to get a good run difference, which translates to a good win number and a good chance to make it to the playoffs. Then here, okay. Another way to write the prediction is to write it like this. You get all the coefficients, then you multiply by all the all the coefficients and multiply by the values that you substitute in. So in this case, all the values we substitute in are this. So and the coefficients are this. So let's just take a quick look. So here are all the coefficients on this line, the estimate line. These are all the coefficients given, and we substitute in these values for the coefficients. So it would, that's all. Coefficients and values. Yeah, so writing this way is, I guess, safer, since the values you get for the coefficients, like, less likely to make a typo rather than typing it down so many times. Yeah, just as a general rule, if you can type it down fewer times, you are less likely to make a careless mistake. Then here optimization, again we just substitute in all the OBP and SLG. We just substitute in all these values and multiply it by the coefficients. Then this would be the run scored prediction. So if they had a salary requirement and a run scored prediction, we would just pick the one that gives the best run scored for the salary. For example, this number 2 requires a lower salary than number 1 and he's able to get more runs scored based on our data. Person number 5, low salary requirement, high run score. So person 2 and 5 are generally like what we find to be statistically they are better in value for the team. Okay, then yeah, that will be all for today. Additional exercises you can take a look. It's based on this equation here. I think we have seen it in the lecture or maybe in the probability lecture. There's this formula here to calculate the coefficients of the linear regression. Then I just added in some exercise that you can do, so you get a numerical value, so you can have a numerical practice. Just an example on how you calculate the coefficients for the linear regression model. Like essentially here is just I just added in a numerical example so you can check by hand that the values, how does R get the values. I think they are using something very similar to the matrices which I typed out over here. Then you can take a look. I won't be going through this in class. Yeah. Then so this is the same thing as before, just a practice question. Okay, then yeah, so that will be all for today's class.